Hello students, welcome to Sarasa classes. This is Dr. Sakar over here. We are discussing calculation of crystal field stabilization energy. Now over here it is worthwhile mentioning that the splitting of the d orbitals has a significant consequence in the spectral and the magnetic properties. So knowing how do you fill up this T2G and EG set is going to be very vital, and then calculating the crystal field stabilization energy. So in this regard, we would like to say that the d orbital electrons in the crystal field now have a choice of either entering the T2G or the EG set to begin with. So there are two basically opposing forces over here, that is the gap of delta O and another is the pairing energy. So over here the magnitude, we will say, of delta O, which for a given metal varies from ligand to ligand, that it depends on ligand field strength, and P the pairing energy, which is fixed for a metal ion, varies from metal to metal ion. Okay, so P for two different metal ions will be different. Okay, we will see that in a chart. Okay, now these two factors will decide whether or not spin pairing will take place or not. Okay, so over here, say we are considering the d1 comma d2 comma d3 systems. In this dn configuration, the T2G set will have parallel electron spins, and this will be true irrespective of the field strength. So whether it is a strong field ligand or a weak field ligand, arrangements for D1, D2 and D3 will be as I am showing. So basically 1, 1, 2, 1, 2, 3. So it is basically obeying Hund's rule of maximum multiplicity and Pauli's exclusion principle. As simple as that. So over here, if you calculate the CFSE value, okay, suppose this level is having n electrons and this is having m electrons, and you know each level over here is 0.4 delta O minus, obviously, and this is plus 0.6 delta O, that into m. So basically you are having over here what? 0.4 delta O into n plus 0.6 delta O into m. So if we use this formula, then my value comes out to be, for a D1 system, it will be coming out to be, I will say, for D1 I am having 0.4 delta O, for D2 I am having minus 0.8 delta O, For D3 I am having 1.2 delta O. Again, for D8, D9 and D10 system, here electrons can be arranged in one way only. That is with one, sorry, two, one and zero unpaired electrons. In EG set. So now if you want to show these arrangements, what will you do? Similarly, like that you have your D8, that is your D9, and that is your D10. And you fill up the electrons. So this is T2GEG, that is T2GEG, T2GEG. So here we have 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9. So one unpaired electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So accordingly, if we calculate now these CFSE values, okay, what we will get over here is out here it will be at this level we'll be getting what? 6 into minus 0.4 delta O, okay, plus 2 into plus 0.6 delta O, and that should give you the value to be as minus 2.4 delta O, alright, plus 1.2 delta O, and that is minus 1.2 delta O. For the next one, it is going to be 6 into 0.6 delta O plus 3 into 0.6 delta O, and that should come out to be minus 0.8 delta. That is 24 minus this is going to be 24 delta O plus 1.8 delta O, that is minus 0.6 delta O, and out here it will be minus 2.4 delta O for the lower level and plus 2.4 for the higher level, so it will be coming out to be 0. So D10 system will be having 0 CFSE. Okay. Now for the next part, in which we will be discussing D4, D5, D6, wherein there is two possibilities. That is maximum number of unpaired electrons and minimum possible number of unpaired electrons. So we'll be taking up that case in the next part of the lecture. Thanks for listening. Have a great day.